So first we'll look at adding functions, and we've seen this already, okay? We've also seen the nice notation and the not nice notation, but we have to be familiar with both of those. So if we have a red graph plus the blue graph, we will get this green graph. And the important thing to notice is since the domain of the red graph is restricted, the domain of our green graph is restricted as well. Subtracting fractions. Again, pull out our highlighter. Nice notation, not nice notation. Same thing. We have our green graph will be restricted because our red graph is restricted. The domain of our green graph is also restricted. Right? If I did f of 2 minus g of 2, remember in the not nice notation, this could show up like that, f minus g of 2. And if you ever see the not nice notation, I just suggest switching it right away to the nicer notation that you're more familiar with. Because this can get confusing. People start multiplying things by 2. No. You see f minus g of 2, write f of 2 minus g of 2. And multiplying. Nice notation, not nice notation. Again, we've done a couple of these already. And just like adding and subtracting, if the original function, the red one here, is restricted, then your new function would be restricted as well. Some key things for multiplying. Okay. When you get to multiplying, when either the red function or the blue function are equal to 0, then your green function is going to be equal to 0 because you're multiplying. Other things that I want you to notice are when either your red function is 1 or your blue function is 1, those will be the places where your green function intersects the other graph. Does that make sense? Because multiplying by 1 doesn't change the value. So when the red function is 1, your green graph will be right where the blue graph is. Where your blue function is 1, your green graph will be where the red function is. So we get to example 1 here. And they're not asking us to graph in example 1. They give us two functions. F of x is x plus 2. That's a straight line. And g of x is the absolute value of x. So you have an idea that this is a line with a positive slope. And your absolute value graph looks like this. So in part A, what's the domain of f of x and g of x? Well, if I do f of x in green, the domain is everything. If I do g of x in blue, there's no non-permissible values in an absolute value graph. Your domain is everything. Given h of x is f of x plus g of x, write an explicit equation. So there we have an important definition. If we don't know what an explicit equation is, it's very hard to write one. Oh, did it ask for the range? Thank you. The range of a line is everything. The range of an absolute value graph, oops, that one's in blue. Y is bigger than or equal to 0. Part B. What does it mean to write an explicit equation? An explicit equation doesn't have function notation in it. So right now, this is not an explicit equation because it has function notation in it. To write an explicit equation for h of x, that means you have to have only x's on the right-hand side of your equation. So only in terms of x. So instead of writing f of x, I can write x plus 2. And instead of writing g of x, I can write the absolute value of x. And with this, we want to determine domain and range. The domain is the easy one. Once you've written your explicit equation here, you look at h of x and say, are there any non-permissible values? Anything you're not allowed to put in? No. So that would mean our domain is everything. The range, on the other hand, is harder to tell, especially if this, sometimes you'll get something that you've seen before, but we've never seen x plus 2 plus the absolute value of x before. So I'm going to show you that you could take your graphs, right? What color did I said my green graph was x plus 2. Would you agree that that's that straight line with a slope of 1 and a y-intercept of 2? And I said the blue graph was the absolute value graph, which looks like this. Now, mathematically, if I wanted to add these two functions together and create my h of x graph, which I will do in black, what's it going to look like? Well, let's take some values. Here, 1 plus 1 would be 2. Here, 0 plus 2 would be 2. Here, 0 plus 2 would be 2. If I went one more value here at negative 3, I would have negative 1 on this graph and 3 on this graph. Negative 1 plus 3 is 3. Interesting. Does it appear that this side is flat? Yes, it is flat. On the right-hand side, if I would take this point, which is 1, and add this point, which is 3, I get 4. And next, if I would add this point, which is 2, and this point, which is 3, is that 3? No, that's at 4. 2 plus 4 would become 6. And then looking at our black graph, and it's only by looking at our graph are we able to tell at this point that the range is bigger than or equal to 2. That is a weird graph. If we wanted to figure out algebraically why this happened, I'm going to teach you a little bit about absolute value graphs and a different notation for absolute value graphs. So this is just a little aside. And I'm going to teach you about piecewise functions, something that comes up in calculus. And the most common piecewise function is the absolute value of x. Now, we learn absolute value of x as a single function, and it is a single function when we write it like this. But when you look at the absolute value graph in blue, can you see that your absolute value graph could be described as two lines, one with a positive slope and one with a negative slope? And so another way of writing y equals the absolute value of x is to take it and break it up into two pieces and restrict the domain in those two pieces. Can you see that this piece, which I'm going to highlight in yellow, that piece is when x is bigger than or equal to 0. And I'll highlight that in yellow to correspond to that. And this part, which I'm going to highlight in green, That part corresponds to when x is less than 0. Okay with that? Question? It doesn't matter which one has an equal sign, but because it's supposed to be a function, we should only define one of them when it is equal to 0. That's fine-tuning information. Okay, so how would we describe it when x is bigger than 0? When x is bigger than 0, what's the equation of that line? X. How would we define the green part? What's that equation? Negative x. And so this is an absolute value as a piecewise function. And so now, if we wanted to, we can now write h of x, which was x plus 2 plus the absolute value of x, as a piecewise function. What would it look like? Well, we have the one piece where it's bigger than or equal to 0, and the one piece where it's less than 0, because that's where the absolute value is separated. So when it's bigger than or equal to 0, what's the absolute value of x? It's just x. And if I would add x to x plus 2, can you see that you would get 2x plus 2? Okay? And when x is less than 0, my absolute value is negative x. And if I would add negative x to x plus 2, can you see that I would just get 2? And the piecewise function really explains the graph that we got. Because everywhere where x is less than 0, it's equal to 2. Did that show up on our graph? Yes, straight line at 2. And everywhere where x is bigger than or equal to 0, it's the line 2x plus 2, which would have a y-intercept of 2 and a slope of 2. And sure enough, that matches up with our graph. So there is an algebraic way to find out what the graph is going to look like, but we have to use something called piecewise functions. Did we use that before? Did I show it to you with absolute values? Maybe. I don't remember it in trigonometry. So part C, we now want to do P of x is f of x times g of x. As an explicit equation, f of x was x plus 2, and g of x was the absolute value of x. So that's writing it as an explicit equation. There's no non-permissible values, so your domain is still going to be everything. To figure out our range, we would either have to graph it or use our piecewise function. So as a piecewise function for p of x, because the absolute value is split up when x is bigger than or equal to 0 and when x is less than 0, when x is bigger than or equal to 0, the absolute value of x was just x. X times x plus 2 would be x squared plus 2x. When x is less than 0, the absolute value of x was negative x. So then you would get negative x squared minus 2x. If I wanted to, I could use my original graphs here to multiply. Okay? And we could see what, right, 0, wherever there's zeros, 0 times anything will be 0. If I take this point, 1 times 1 will be 1. If I take this point, 1 times 2 will be 2. If I take this point Negative 1 times 3 would be negative 3. And it looks like this, which kind of looks like an x cubed graph. But in fact, this part's here like this. It's a little bit different. And you'll see why it's a little bit different because I'm now going to graph it as a piecewise function. Okay? If you're graphing something as a piecewise function, just get that so we can see it. I'm going to color code things here. I'm going to graph this in green, this in blue. How do you graph x squared plus 2x? It's a parabola. I would probably factor it to be x times x plus 2. And in factoring it, I would find out that I have a 0 there and a 0 at negative 2. Which way does that parabola open? It opens up, so I would also have this point down there. And I'm just going to graph this whole parabola with a dotted line. That's the parabola of x squared plus 2x. If I do the same strategy for, oh, I did the wrong colors. That's the blue one. This will be our green one. If I do the same strategy with the green one, I would factor out a negative x, and I would find out I have the exact same zeros, but this parabola is going down because we have a negative x squared, and it looks like this. What does my final graph look like? And I'll do my final graph, the whole thing in purple. What it says is it says take a piece of the blue graph and a piece of the green graph. Which piece of the blue graph will you take? Only when x is bigger than 0. That's the piece of my blue graph. Which piece of the green graph should I take? Only when x is less than 0. And so this is the graph of p of x. And initially, we made our graph look very much like an x cubed graph. Can you see that it's a little bit different? Because it's a very sharp bounce kind of point right there. Not smooth bounce like we're used to, but it's a sharp point at x equals 0. So the graph is a little bit different. Okay, questions for practice. 3, 5, and 10. Oh, by the way, now that we've graphed it, we can see that the range of our purple graph is everything.